In this video, we'll be talking about diffraction, holograms, phased array antennas, and a remarkable physical theory that ties them all together. This is Speaking Physics. Welcome to my home office. This is where I've been spending a good deal of my time over the last several months thanks to the coronavirus. Behind me here you'll see a plain wall. It's not very interesting. I've been meaning to do something, put something there, maybe a window. But the problem is, as it is an interior wall, all it would reveal is the next room over. But what if there were a special paint that I could paint a window onto the wall in such a way that I could look outside? Well, you may say that that's impossible. After all, if we just paint a picture of a window onto a wall, it would look flat. There'd be no depth. And if I were to move my head from side to side, there'd be no parallax effect. It just wouldn't look real. But one of the amazing things about physics that I want to talk about today is that it is possible, in theory, to paint the wall in such a way that it would be indistinguishable to actually looking through, looking out, and seeing the outside. Now, unfortunately, this remarkable physical result has a rather bland-sounding technical name. It's called the Electromagnetic Surface Equivalence Theorem. Now, in our case, the paint that we use is actually an electrical current. We'll call the density of that current J. These are the same kinds of currents that we have in the wiring in our houses, albeit at a much higher frequency if our paint is to be used for visible light. Say we have a flat wall with a window separating the outside from the inside. You'll remember that light consists of electromagnetic waves involving an electric field E and a magnetic field H. In particular, the light from outside the window will produce certain electric and magnetic fields. Our goal is to replace the real window with certain currents in such a way that the fields inside are exactly the same fields that would be produced if the window were really there. The currents needed to do that can be expressed by a surprisingly simple equation. First, take the unit vector pointing from outside to inside. This will be called our normal vector, or n hat. The current J that we need is simply the cross product of the normal vector and the magnetic field H multiplied by 2. That's it. Now, if I'm sitting inside the house, I have absolutely no way to tell if I'm looking through a window into the outside or if I'm just looking at a plate with some electrical currents on it. Now, we could end the video here, but this simple equivalence principle has some very practical applications in understanding physical and engineering concepts. So let's keep pressing. Pick an observation point R, a good distance away from the window. The currents produce an electric field that can be expressed in terms of those currents that we just defined. Assuming the polarization of our light is perpendicular to your screen, we can write the relationship like this. Well, that looks a little more complicated than the simple equation for currents, J, but it's not too intimidating. Let's walk through the important parts together. J is just our current from before at some location R'. Big R is the distance between R', where the current is, and R, where the observer is. So this term means we're just taking the phase of the current and rotating it clockwise by an angle proportional to the distance, big R. The constant of proportionality, K, is 2 pi times the frequency of the radiation divided by the speed of light. The integral sign just means we're adding together the contributions from all the currents in the window. It might be clearer if we used a picture. Let's assume all we had outside was a plane wave coming straight through our window. Think of it as a point of light infinitely far away that's shining some light through the window. That means that the fields and J will be the same everywhere on the surface of our window. So the only thing that's changing is this phase term. Let's draw some arrows to represent the contributions from each current segment along the window. The phase of each contribution is equal to the angle of the arrow. If our observation point is directly in front of the window, the distance to each point on the window is approximately the same. Yes, I know it's not exactly the same, but remember that we're assuming our observation point is really far away. That means all the arrows will have the same angle. Now, what happens if I move my observation point to the right? The distance to the center of the window hasn't changed, so that phase will stay the same. But now the points on the right side of the window are a little closer. That means that big R is smaller for those points, so we have to rotate the contributions from the current on the right side counterclockwise by a little bit. Likewise, the points on the left side of the window are a little farther away, so we have to rotate those contributions clockwise by a little bit. You can probably guess what will happen if we move our observation point to the left. Now it'll just be the opposite. The arrows on the left now rotate counterclockwise because they're a little closer, and the arrows on the right rotate clockwise because they're a little farther away. Now, remember that the integral means we'll end up adding these little arrows together, base to tip, to get the total electric field. The total electric field amplitude is given by the distance between the base of our first arrow and the tip of our last arrow, which we'll show using a red arrow. To help us keep track of the length of that red arrow as the observer moves, we'll trace out that length with a blue line. Now, watch what happens when we move our observation point around. We shouldn't be too surprised that we get a large total amplitude right in front of the window, since that's the direction that our plane wave is shining directly through our window. But we don't get zero amplitude everywhere else. There seem to be particular angles where the currents combine to get a fairly significant field. This is because of diffraction. We can make this even more apparent if we have 2 windows instead of 1. Now our arrows look like this when we move our observation point around. We rotate the vectors as our observation point moves using the same rules as in the previous case. Again, we'll add all our arrows together and watch how the amplitude of the total vector changes. Now we see even bigger fluctuations in the radiation. Of course, all we've done here is to replicate the double slit experiment. So, by taking our window and replacing it with equivalent currents, we've found a way to conceptualize and calculate diffraction. One other thing that's interesting from a mathematical point of view, but not essential to the rest of this video, is the role that the Fourier Transform plays in this process. Let's again revisit our formula for calculating the electric field. If the observation point R is far away, we can approximate the distance, capital R, in terms of another variable, u. To calculate u, we draw a unit vector from the center of the window to the observation point, and then take the horizontal component. R0 in this equation is the distance from the center of the window to the observation point. The reason this simplification is helpful is that now the equation takes the form of a Fourier transform. The electric field, as a function of u, is the Fourier transform of the currents J. So for example, in our first case, when the uniform plane wave is illuminating a single window, the current distribution is just a rectangle function. The Fourier transform of a rectangle function is a sine x over x function. And if you take the amplitude of that function, you get exactly the same shape as the one we got when we added all of our arrows together. We can do the same thing for our double window experiment. Taking the Fourier transform of a double rectangle leads to a sinc function, sine x over x function, multiplied by a cosine function. And again, this is the same thing that we got by adding all of those arrows together. In fact, in the past, scientists have exploited this relationship to use optical diffraction to rapidly calculate Fourier transforms. So, enough about Fourier transforms. Now, you may be asking, if we can use electrical currents to create artificial windows, why don't we see them in our houses and everywhere we go? Well, it turns out that at the frequencies of visible light, it's very hard to make those currents oscillate quickly enough and precisely enough to create this coherent effect that we need for the artificial window. But there are a couple of exceptions. One is just a mirror. Have you ever wondered how these work? Well, the light from the room hits the mirror and induces electrical currents in the surface of the mirror, which acts as an electrical conductor at the frequencies of visible light. And if the surface of the mirror is smooth enough, those currents turn out to be the same as the equivalent currents that will be needed to create this artificial window reflecting the scene around it, the scene in front of the mirror. Another example is a hologram, and in this case the electrical currents are controlled by very small geometric fluctuations in the surface of the hologram. Okay, now there's one more example where we can actually create this effect using ordinary electrical currents traveling through ordinary wires, and that's the case of a phased array antenna. Here I have my little model of a phased array radar. And if you look at the aperture here, if you look really closely, you can see these little dots. Those dots are actually antenna elements, little antennas comprising the big antenna. And because the currents on each of those antenna elements can be controlled independently, it's actually possible to think of this as equivalent currents to create an artificial window into some outside world. And so if I wanted my radar to send a beam of radiation off in that direction, all I would have to do is imagine in my virtual world back here some source of light that is beaming energy in the direction that I want it to go. And then to calculate the effective currents, I just use the equations, the formulas that we reviewed earlier in the video, put those currents on the antenna, and to an observer standing where you are, it's impossible to tell whether I'm looking at a plate of currents or through a window into some virtual outside world. How cool is that? Thanks for watching. We'll see you next time.